everybody's here. I don't really need the mic. I'm really loud already. So my name is Dennis Cox, and I'm going to talk about, I spent most of my career so far building boxes, so routers and switches and IPS and all that other stuff, and now I take them apart. So it's kind of fun, and I'm going to talk all about that today. Most of what I'm going to talk about is my anti-campaign on architecture. For those that don't know what architecture is, it's when the marketing guy designs the architecture. So that's called architecture, and it's really crappy, and people do it all the time. Like when we were at Tipping Point, I was there for 6.5 years, so a long time, and we built a product we called it IPS, and then all the IDS vendors came out and said, that'll never work, that'll never work. And we got market share, and they all became IPSs. Architecture.
And it still doesn't work.
Yep, I'm sure it doesn't. Everything's supposed to take my box. So, anyway, they just redesigned it, they didn't re-engineer it, they just put new stats on slides. And that sucks, and I hated it. And so, I'm going to talk about why they do that. I'm also going to talk about some products, like, anybody from ISS here? Good. Anybody from Juniper here? I know there's like one guy, yeah, sorry. Anybody from Top Layer? So those are going to be my 3 examples. I found a good Juniper on eBay, and I took it apart, and I'll show you that. So we're going to try to separate the fact versus fiction of today's network security products. So
were you doing it for compatibility reasons?
I was doing it for interoperability for my slides. So the fact versus fiction of what's real, what's not, what they say on the slide, and you have some simple Chris Abad style math to get there. And Chris, what's up, man? So we're also going to talk to you how to go figure it out. Some reading some stuff, and then give you some examples. So. First thing you want to know when you open a box, whether it's a router or switch or a VPN or a load balancer or whatever it is that you're buying, is it's hardware or software. And what I mean by that is there's hybrid boxes which are a little bit of hardware, a little bit of software, a little bit of text, a little bit of this. But it's really easy to figure out. Just look at the box. Look at the mechanical design. Is it a 1U Dell server with the logo missing with ISS replaced with it? Yeah, probably not hardware. Also look at who runs the hardware team. Hardware is tough. Hardware is not easy. You generally have a double E doing hardware, and if the guy that runs the engineering team is some reverse engineer or probably some software guy writing in Java, he's probably not doing hardware. I don't know, Java to silicon doesn't really work. Also, take a look at what silicon they're using. Companies love to do press releases, and they do press releases on everything, like you just bought some more of my chips, or you didn't buy more of my chips, or whatever. And so you can figure out what a company's doing just by looking at their PR campaign. Like at Tipping Point, we made a big announcement about Xilinx. How many Xilinx FPGAs, we use them a lot, so you can tell that we use FPGAs. I haven't seen one from a couple other companies. Also, the size of the company, hardware requires manufacturing, manufacturing requires operations, operation requires a bunch of overhead. It's got to be a pretty big company. If it's not a good sized company, probably above 100, and I don't mean like sales and marketing people, because they're busy doing architecture, they're probably not doing custom hardware. They might be doing a subcontractor, but they're pretty easy to figure out. And check for posts. I find that Usenet, especially for next screen, Usenet is really, really interesting about people having trouble with Ethernet drivers or different things around it. And you can just check Usenet and watch the developers post. I'm using Linux, I'm having trouble with this. Well, they're not using hardware. So it's another good tip to use. So hardware is a little tricky. So we're going to break down hardware. I'm going to build you a little virtual device of how hardware works, so you can spot it and exploit it. And yeah, that's my little quote there. So it's kind of gay, but it's all right. So we're going to talk about that. Then we'll talk about software, and we'll talk about how that is. So our virtual device is like so. And this is kind of what any hardware box would look at. You could put a Cisco box. This is what it kind of looked like. And things aren't really hooked up correctly, but the management processor could also be called the data plane processor. A lot of companies reuse them, like Cisco does. The management processor and the data plane processor are the same. Some companies, there are multiple data plane processors and a single management processor, kind of like the Introvert box or McAfee. They have that kind of style. But I just put it here for simple reasons. So we're going to go over each one. The cool thing about Ethernet Max, if a lot of boxes, they have multiple Ethernet ports, they're using a switch, right? There's only really 2 manufacturers of switch chips, Broadcom and Marvell. So if you find a bug in one, you found it on every box that uses the Broadcom. If you find a bug in Marvell, you find it on every bug that uses the Marvell, which is great because you really don't have to worry about the box itself. You just attack the switch chip. The switch chip comes first, and they even use the default drivers and stuff like that. So you can really have a lot of fun with that. So look at the vendor, figure out who it is, and then look at the specs. A lot of times you'll find out that the Ethernet chipset is, can only be rated at 500 megabits, but they're selling you a gigabit box. So that might kind of tell you that you're not going to ever get gigabit speeds out of it. Or they'll tell you that that Ethernet chipset only supports, I don't know, PCI, and they tell you that they can go 10 gig. It's probably not going to work either. Also, for the revision of the chip, me and Toby had a conversation about this at CanSec, but you can look at the revision. Silicon is labeled in a certain way. I know Lenny went over this the other day, but one thing that's missing out of that was revision number. A0 means that it's fresh off the line. So if it's fresh off the line, it's feature shift. And so you can pretty much do anything you want to that box. It takes a large number of revisions to get any chip right. I just ask Intel. So you can do that. And eSIG also works pretty well. One of the big things I noticed is that I'm lazy, and a lot of people are lazy around me. And so if someone hands me a pile of free Darius driver code, I'm just going to use it. Now the vendor wrote this as sample code, and some guy in like Bangladesh strapped to a chair and whipped every hour how to write this code, and pretty frustrated, and he's not too happy. So it's pretty shitty code, and so everybody uses the same code. A great way to do it is go to like Broadcom's website or Marvell's website and download their sample code. It's awesome. Some of them have embedded channels for management, which means that the guy that makes this box, includes a switch chip, doesn't even know that you can manage his switch chip remotely. So that's really, really cool stuff to do. Like, you could turn on all the VLANs, you could do things like leaking. That's a great way to do leaking, so it works really well. We're going to talk one more thing about Ethernet, because I want to make sure everybody understands this topic real quick, and then we'll move past it. Everybody knows how it works. There's a thing called inter-packet gap, all right? And I won't go into the boring details about it, but basically, it takes a large number of frames to get, smaller the frames, it takes a large number of them to fill a gigabit. And in fact, you can't even hit a gigabit at 64-byte packets, because you have inter-packet gap. So basically, you got to do 1.5 million frames a second, and you get a little over 750 megabits. So as you decrease the frame size, of course, the packets get bigger and it's easier to deal with. This is really important between hardware and software, because hardware, it's no big deal. Software, there are interrupts, and as we know, there's only a certain number of interrupts there can be. So this is interesting. Keep that back in mind. Next thing we'll talk about is CAMs. CAMs are content addressable memory. Basically, what that means, it's a big old hash table, some kind of sort. It's got a certain number of bits wide and a certain number of bits deep. So you can go figure out from the vendor, look at the part number, you can do what Bunny showed you, and you go on Google and get the part number and find out, hey, how big is this CAM? It's this wide by this much. So that's what they're doing with it, right? It could be for 5 tuples, it could be for natting, it could be a number of things. They're semi-programmable, meaning they can only do certain things, but they're really, really fast. But the cool thing about CAMs is how people handle exception processing off CAMs. So if the CAM runs out of space, what happens? It goes to software for some exception processing. Or you can overflow a CAM really easily. You probably saw tons of Cisco switches bugs on 6500 of people overflowing the CAM because they had 4,096 entries in the CAM using MAC addresses, right? And basically they had like Dell had large equipment behind that one switch port. And so it had more than 4,096 CAM, so it couldn't keep up, and so all the packets were going through a processor, which is really, really slow. So watch out for CAMs. Field programmable gate array. This is the first conference I've ever been to where people talk about this a lot. So that's awesome. The thing I want to say about it, they're just processors. They originally were made so that you would, test your thing before you went to silicon. So you write the code on the chip and then you bring it out and crap it out. So that's how it works. They're really programmable. The big thing about them is they're state machine driven and the parsing engine. So if they deal with packets, the parsing engine is pretty crappy. So the reason it's pretty crappy is some security guy like Pedram will say, I need this. And then some software engineer, will say, well, this is what he needs. And then he'll write some requirements document, and some design engineer will implement it. Now, a design engineer has no idea about software, and he has no idea about security. So he goes to Stevens' book, he looks up, page 13, UDP, and he types in, this is what UDP looks like, and here's how you do it, and let it keep state. Here's TCP, and he does it exactly. And so when he does it exactly, that means he doesn't handle all the error cases. He can't. Now, the good thing about FPGAs are they're really, really fast. So if you do an FPGA, they're going to work really good, but they only work in the context. It's really small context of what they can do. So they're really easy to beat up. Also, they have a weird QA cycle. There's usually a test harness they write to test the FPGA. And that's not like QA. So you usually can find stuff. All they're testing for is valid input, valid output. They don't do the normal, ISIC. So you can kind of do that on it. Network processors, these are my favorite. I love these things. Basically, they are fixed field pattern matchers. They are basically an FPGA made in silicon that only deals with networking. There's some that work really well, like the gear. I'm a big fan of that one because it has a functioning programming language and it does fixed fields. Find me the TTL field and tell me if it's greater than 4 or greater than 16. There's other ones like the IXP, which Intel just killed, which is more like a regular processor. So there's lots of different ones. They're really bad on memory. A good thing to do is send really large flows of TCP because you can't store all that memory. Or send fragmented traffic at it. They really don't work well like that because they have to store large amounts of buffers to reassemble the frame and find out where the field is. So you can make them overflow. Now, anytime you make anything overflow, like an FPGA or a CAM or a network processor, it has to be handled by something that can be general purpose, like a processor. You can get to the processor, you get good stuff. The management processor is generally like a Pentium. You'll see like a PowerPC on a lot of platforms, or a RISC or a MIPS on Cisco box. It's pretty easy to figure out if someone has a management processor or a general purpose processor in the data plane. And the way to do it is just, if you talk to the management interface, do packets slow down? So like do a large query, like some SQL query against the box or something like that, and then watch the latency of packets. And if they slow down, you know that they're going through a general purpose CPU. So no matter how much hardware they have, it may not really be useful because it's just going through the CPU. They're really bad on memory also, so you can use that. But most thing is, almost everybody has an exception processing. Maybe one of those Linksys hubs doesn't, but most everybody does. And so you can a lot of times root a box that is a transparent mode box by going through regular network. So you wouldn't expect to do that, but like look at WittyWorm. That was a great example. Like they used the ICQ protocol encoder to fuck that up, so it didn't work for them. So the buses. This is an easy part. So if somebody has like a 10 gig switch chip in the front, and then someone has like a 2 gig cam and huge stuff, but they have it all hooked up to an ISO bus. It really won't run that fast, right? So a lot of times I'll take apart systems and I'll look at things and I'll see this awesome card. I'm like, wow, that thing is awesome. Like Juniper box, it's 4,096 descriptors on each card on E1000 using the silicon bypass. Yeah, I know. So they have it on PCIX, except they didn't compile the kernel with PCIX. They just compiled it to PCI. So that was, 133 megahertz. Didn't work as well as they probably could have fixed that drive driver. So buses are really interesting because whatever the slowest bus is how fast the packets will run. So if you look at the board, take a little flashlight, look around, just find out what buses are there, or look at the chips and find out what buses there are. You can figure out a lot of things. So we also have an interesting thing is they have a max frame size and max frames equal performance, kind of like Ethernet. So you can figure out how often a bus can transmit and how it can do things that way. So we're going to do a little math on buses. This is mostly to pick on the software platforms. So basically, I got this actually from Dell and Intel's website for like people that want to buy their stuff to redeploy them, And there's the stats. And so basically what we find out is if you got 133 megahertz PCIX, you're going to get some fast stuff. And if you got PCI, the reality is about 972 megabits. So that's pretty good. That's a pretty fast amount, but it's not a gig. So whenever I see 33 megahertz PCI, I know if I buy a gigabit box, it's not going to run a gig. Because it can't, because theoretically, it doesn't. So, man's got no limitations, right? Software. So, let's talk about connection map. This is all setting up to the other four guys. Anybody want me to really scream loud again? Right, okay. So, 70% of traffic is TCP. Location matters. I grab these stats. You could pull any number out of your ass if you wanted to, but basically that's generally what's out on the net. Corporate America, average TCP size about 512 bytes. The truth of the matter is they're all below 70 bytes and they're all about 1,400 bytes, right? They're on this side of the equation. Only the packets at the end, put it this way. Now this is not always true for all applications. I'm talking about primo applications. So 1 gigabit, 512 bytes equals 244,000 connections. So that means when you buy a firewall that's a gigabit that supports 5,000 connections a second, it's not going to work. Right? It's obvious that gigabit, 244,000 connections, not going to be good. Since TCP7 requires 3 packets of 70 bytes, which means you got about 1.4 million connections per second happening. So 1.4 million connections per second. Anybody know any firewall out there today that does 1.4 million connections per second? No. So how can it be gigabit? It's architecture. So no one did the math. No one figured out that a gigabit equals a large number of connections. NetScreen sells a big box right now out there that's smoking. It does 2 million connections and it's 20 gig. So basically, that 20 gig box can support gigabit Ethernet. So that's kind of strange that anybody would do that. And you'll find out if you actually plug them into something. Software, interrupt stats. So as as you know, a CPU can only do so many interrupts per second and off across a bus, and so basically there's a thing called interrupt chaining where they try to cluster a bunch of interrupts onto an Ethernet card. So if you use the silicon, bypass stuff with the E1000 by Intel, and they have set for 4096 receive descriptors and 4096 transmit descriptors on both interfaces. You get 16,000 descriptors. You can do a lot of stuff with that, but basically you can only handle with interrupts on a Pentium receiving from this card about half the gig, half duplex, 1 gig, half duplex. So that's really not a good thing to do. So if you use general purpose processors, you're not going to ever be a networking device. You'll never have the latency that way because you have a problem with interrupts. Sorry. And then harder devices generally don't have this because you can hook it up to an FPGA. You won't have interrupts. You can pass them with buffers. You can do different things like that. So if you're using a Dell, like an ISS box, you're at 761 megabits divided by 2, so that's 380 megabits per second, yet they sell a 2 gig box. So theoretically, they can maximum head is 380 megabits per second. Now the cool thing is, what people have done, and I think this is awesome because this is really smart, is they put a little chip on their Ethernet cards. Yeah, you know what I'm talking about. And they put it right there between 4 hits to PCI bus. And so that if they want to, when they see packets from like a Spirent box, it'll flip over and they'll all go through at line break. Then they can pass tests like NSS. So it's really cool they can do that. And in fact, they'll identify Spirent packets. And that's all they do. I thought, wow, that's a really clever idea. And they pull the chip off. It goes great. Put the chip back on, really fast. So it's a neat trick they do because that same test equipment, everybody uses the same stuff. So we already know they're limited by the bus. We already know they're limited by interrupts. What else do we need to know? So buffers. This is where it gets really tricky because there's only so much addressable memory there is. So if you have too many buffers to to receive on, if you're doing packets in, too many buffers, then you got latency because you have to do some kind of ring or linked list to get to those buffers, right? So you got to walk the chain. The longer the chain is, the longer the walk. The longer it's going to take. Buffers are not mallets because they would be really slow if you had a mallet buffers on every received packets. That's too slow. And they're also set to the max packet size. Why? Because you don't know what the packet's going to be. So if I support jumbo frames, I'd be at 9,000 byte packets. Okay, 9,000 byte packets. It's good to remember. All right. So now if I did fragmentation, hyperfragmentation, you got 64K, right? So I got 9K packets, 64K. Now, if I sent a bunch of small packets in, I would have 9K by 64K, 64 byte packets. I could pretty much fill up a lot of memory really quick. Now if I did TCP reassembly where I do big flows, and I did that while I'd be fragmenting on jumbo packets that were 64 bytes, you could see that you'd take up a lot of memory. So generally there are additional pool of memory, so people have a different pool of memory for TCP reassembly, they have a different pool of memory for hyperfragmentation. If you use like the Juniper box, you would SCIO and set those values, am I right? Yeah. So the attacks over time on buffers. So you can attack anything by doing this half connection attack, right, where you send part of a packet in, and then you wait, fill up all the state, and send the part of the packet out on the other side, right? Everybody has detection mechanisms for that by holding on to attack, or they game the system by knowing a known exploit. That's going to be in the test case. But really, the trick to do it is just slowly eat up the buffer so that no one can have access to the box. Because that's a lot more fun. Because I am a griefer, and I like that stuff. So also, people use regular expressions, they use protocol decoders, like ISS do, and they have really cool protocol decoders, really cool stuff in there. And they take up memory. They alloc memory. So now if I send, let's say a DNS, then I did TCP reassembly, and then I did fragmentation, and I send over jump packets, I take up a lot of memory.
Can you compare some of the different protocol analysis engines that are out there and the pros and cons of the different methods used by some of the different IPSs?
No. So next. Good question. So, I won't do that. I can't give away. I like my baby. The way to figure out how to kill a box, I found the easiest way is to figure out what costs it the most. Whatever costs it the most is going to kill it. Right? So latency is the easiest way. So whatever takes the longest to get through probably went through the most parts. Right? That's pretty easy. And the secret to this whole thing is near missing. Get it so that it blocks it, then back it off just a little bit. It'll eat up the most buffers, and it'll take the engine the most time. So it's really easy to, for example, make a box do 1 packet a second. Because if I get the worst case scenario, I can make it 1 packet a second, which is really cool. Because then, I'm completely legit. I didn't send an attack, and the box is this big 2 gig box I'm going to spend $200,000 on, and 1 packet a second DDoS. It's pretty cool. So we'll do ISS. So first thing we gotta do is ask our questions. I really don't like them, by the way. It's the only people I don't like. So the first question is, what type of box it is? So we look at mechanical design, we look at who runs the hardware team, and believe it or not, they have some great stuff on their website, the management team and all their stuff, and it was a Dell server, because I took my Dell bezel and I replaced it with their bezel, and it fit perfectly. I thought that was the strangest thing. I guess they had the same guy. So they don't actually have a hardware team. They also, the GU1000 had 2 gigabit Ethernet ports. All right, I got it from the data sheet. And so that's pretty cool. 2 gigabits. So I expect to get 2 gigs. But don't forget, when you're a transparent device, you got to do a gig in and a gig out. And a gig coming this way and a gig coming that way. So it's really a lot more than 2 gigs. It's tons. I don't even know the math on that. So basically, they have a PCI bus because it's a Dell platform. Okay, so it's limited to 520 meg, 8 megabits full duplexer, 972 half duplexer. Don't forget, you got to go both ways. And it's really 472 due to overhead. So there is overhead of getting these off the PCI bus and setting it up and tearing it down. So it's never perfect. Specs aren't great. So using software, so interrupts come into play, but it's 368 megabits per second. Now that is on 64-byte packets, so on large packets, I'm sure they do well. They're using 2 controllers. So 2 controllers, it's double the interrupts, so that's 184 megabits. It's a little bit slower. And then they got the double buffering, because you got to come in the buffer and come out the buffer. All right, so basically the idea is a Dell server costs you $3K, ISS charges $36,000 the same level. That's pretty crafty, man. That's just, you got ripped off. You can just go on eDonkey, that guy has that website, you can go download that, put it on your Dell, it'd be great. So another big thing is they do this architecture thing, right? And they talk about like max connections and how does it handle buffers. It's like awesome. They do this. We're rated 1,000 concurrent or 1 million current connections. We do TCP reassembly and flow, and we got jumbo frames and jumbo this. And so I decided to do the math, right? So I showed you the math, 9K, 64K, all right? And I even gave them away with TCP reassembly. So 82 gigabytes of memory. All right, so I don't know any PC that can address that, period. In fact, I don't even think on Linux, it's pretty hard to get 4 gigs addressable memory. I think you have to do some tricks. So that's, they're lying. And that's not good. So, that's not good. So, even that, you know what's funny is, even if they did it, they didn't even hit line rate on single Ethernet, because there's 1.4 million connections. So even though they lied and they suck even more because they didn't even lie to the right amount. Like, I'm going to say it most likely couldn't, because, it could, I guarantee you they're mod in the box right now, the kid to do it. So, you can't address that much memory, it's too much buffer copies, there's no buffer copies, and there's no memory, I guess no one else is here, so I can read out this one.
In order to count on the flash capacitor.
Yeah, that's what they got, 88 miles per hour. So, even if they could handle all this stuff, they need to do 1.48 million more connections because they got to do full duplex. So, the easiest way to attack them, I think, is basically narrow down which area of memory is the smallest, what they're expecting the least of. People do profiling networks. I know we did a lot of work with this tipping point. It was really hard work too. But you have to profile the customer's network, and I don't mean like with the box. I mean just actually go in there with a sniffer and understand what the network is and figure out where you need to make where you need to make your pools of memory. So is fragmentation it? Is it in protocol decoders? What is it doing? And so the easiest way to find it is find the one that has the least amount of memory and go beat that one up. So now Juniper. So I told Hugo and Matt and Gus, I call him Gus, I know his last name, but can't speak any French other than hey baby. So I saw, they told me to get a new box. And I said, okay, I'll get a new box. So I went on eBay, and I always wanted to play with one of those IDP, the Juniper boxes, which is the one secure boxes. And we had one like competitive level, but I never like actually got to play with it and tinker with it. And I saw it on eBay, because eBay's cool, right? And it was like, 4K for the box. And I was like, all right. So I got it home, and I immediately took off the void your warranty stickers, unscrewed it. And the weirdest thing, I give them pretty good credit, but basically, I'll tell you that in a minute. It's a 1 UPC. It's a super micro board, right? Yeah, 2.8 gigahertz. I think it's a Xeon too. I had a tough time telling because I couldn't get the thermal grease off it that easily. I got it all over my clothes. I like clothes. So it also had an ATI Rage, which is awesome because you need video for your IDS. So you can actually look at the monitor. It's crazy. So it was running the 2431 kernel, and it was using the Intel 1000 parts, but they were using the silicon bypass. I give them mad props, because I didn't figure this one one out. We actually had to do it in FPGA. They used a little company that did the bypassing for transparent mode. With that was really well done. That was a good piece of engineering. I was impressed. So there's the box at eBay on my desk, and most of the pictures turned out really crappy because I don't know how to take pictures. So, but you can see, brand new. And so I found some. I went from 3.1 latest release all the way up, so I kept on going up to see what they did, because that's really cool. And they are men. They just threw their balls right on the table. They give you root access to the whole box, right out of the box. And so I was like, whoa, we worked so hard to secure everything, and they just like, here it is. And then you give a manual with the tools to reverse engineer it. And I was like, wow, this is awesome. So they really stepped up. Sadly, the balls weren't really that big when it turned out. They stepped up. So, hey, may not be able to see them, but at least they're there. So, the IDP box. I found it really odd as well. I looked at the architecture, and you correct me if I'm wrong. They had the 10, the 50, the 100 megabit, the 200 megabit. I'll show you how to get from a 50 to a 600, which is really cool. It's a software tweak. And 500 to 600, 1,000. And I realized that they never went really past the full gig mark. They kind of stayed below where it was beyond the FLNB software. Now, NetScreen is known as a hardware company. They made hardware firewalls. I literally burned the namesake. They made hardware and really good SSL stuff, really hard stuff. Juniper is the same way, hardcore. But OneSecure wasn't. They were an IDS company. They got re-architectured into an IPS company, which is like, whoa. So it was interesting. Another thing I found interesting is that they sell a large number of descriptors. So more descriptors is good, but also leads to a little bit of latency. So it was definitely an IDS to begin with. So there's the inside of the box, and I think this is the laser pointer, right? Where's that click thing? Oh, the click thing. Never mind. So there you have your little, your Pentium 4. And you can see here they made a little channel so the airflow goes through right here. And then you got your 1 gig of memory, and you can upgrade to 2 gigs. That's when you want to go to the 600. And then you can go over here, and this is your PCIX card. And it was PCIX, and I was really impressed. And then kind of saddened because it's cool that they have PCIX because that's the right answer. Absolutely good job. Awesome, way to go, engineering. Like I said, you guys did a good job on my card. Except you put it in the low-end platform. You only said this was 50 megabits. You spent a lot of money to do 50 megabits. 50 megabits is not that big of a box. This is a little Quanta CD-ROM drive. They actually have a CD-ROM drive built in. So you can actually take the kernel and load it. But the box is really loud because this is a super micro, and it just turns on the fan constantly. Like nonstop. And the guy, he's in the office, and he's like, turn off the box. So I had to do something else. So I'll talk about that. It also has a management server. You have to install like a separate Linux box. Now it's too cheap, so I actually installed it on their box itself. So which they tell you can do, which is pretty cool that you can actually install the management software on the. And anyway, there's 2 commands you need to use when you're using a Juniper box, and that's the SCIO and SCTOP. IO lets you set the commands, and top lets you kind of see the performance, the monitoring of everything. And it's great because Microsoft has these encrypted signatures now. Everybody knows about that, right? Where they have a special deal on the table. Come on, Bill. Where they get the 0 days and they give it to all the vendors, but you have to encrypt it. Except when you put it in memory, you give me SCTOP, and you just watch the filters go by. So that didn't really work well. But it's really good because now I can reverse all the Microsoft sticks because they're clear in memory on all these boxes. So just dump memory, you can see them all. It's pretty cool. And they're regex, so you can just figure out what they're trying to do. But you can also attach and watch, which I did. So since they give you access to the box, you attach debugger and get all the symbols. And you don't get the symbols, but you get the assembly and just watch a packet go through the entire box, which is pretty cool. It has 7 processes running, so it's really busy. So the box is loud, so I ran it in virtual PC, because that's custom hardware for you. Because when you can run it in virtual PC, yeah, you take the disk, kick it into the drive, and man, it worked. I was like, wow, this is awesome. I have an IPS running, and it turns out you can do this a lot of them. So, now you can just copy these, put them on eDonkey, and everybody can have NetScreen. So, I have to say that this was actually, you're not going to believe it, but it actually is true. I wasn't an IDS fellow. I didn't really believe in IDSs. I thought that was kind of gay. And so, and when we built an IPS, we didn't really want to call it IPS. We were building a security box, and we were doing it very, very focused, which was, code red's code red no matter what you do. It's pretty easy to spot. We weren't looking for things like someone ping, GA. So I really cared about, we cared about matching exactly that packet. It never occurred to us, but IDSs, we weren't IDS guys. We were firewall and router and switch guys and ATM guys. And so I booted this thing up, and I had my Mac, and I had my like old Sony file when they were hip, and I had that over here, and I had the NetScreen box, and hooked up, and right away I get 2 alerts. I'm like, wow, my network's infected. And one of them was that IGMP v3 DDoS, so I really thought I was in trouble. And the other one was a PuTTY overflow. I was like, oh my goodness, and it dropped it too. That one just alerted, that one dropped it. So I was like, immediately had to figure out what false positives were, right? Well, I didn't think they were false positives, I thought they were real, because I never saw false positives, because I didn't build that kind of thing, so I looked at them, and their signatures are broken up into 2 things. There's a context, where it takes place, like in the SSH header or the HTTP header, and then there's a regex. So they have a cool context, because you can have dual context, right? You can have context going this way, and context going this way, different regexes, and they're really cool. And they use PCRE, so that's a little fatal flaw, but supposedly they might have another one, so. Basically, the IGMP alert was that my Mac booted up and did a request with an IP option, and that kind of alerted it. So IP options, IGMP, okay. And then the SSH one it was PuTTY, and there's the sig right there. It's SSH2O PuTTY. You know, there's packet null, and it was weird because they said it was B005 a PuTTY, and I had like B007. I was like, hey, what the hell? Why is it firing on this? And so I was really like, wow, what's going on here? You know, I thought this was like, you know, Juniper's a big guy. So it was all regex with digs. Count how many things there are. I should give you an answer to the recursion in a minute. How does it handle recursion, right? So I'm going to take all the exploits that we have. We have all these custom exploits, and I'm gonna send them through first, and then I'm going to put all this recursion stuff on it because I'm really good at that stuff. I'm going to send it through, and I'm going to beat everything. This is going to be great. Make a great talk, and it's going to be real stuff you read about now. And so the first thing I'm going to show you is they like I said, they manned up, right? And so there's their fast path, which is our data plane, like get things quickly to the box, and there's their slow path, which means I had to look at it. And then here's like the policy hit and miss, so you can start seeing where your near misses are, and where you went through things, and when you had to do the packet log, and all this stuff. And they have tons of these out here. I mean, you guys are chock full. I mean, it's really cool. I mean, you get the whole inside. But this is really interesting because more boxes went slow path than fast path. It's got to get the opposite way. And then here's their top, and I know this is really hard to see. You don't really give a shit about any of this stuff right here. PCRE recursion limit, 7. So if I give you a certain number of recursion depth on your filters, if I know your filters, I can just bypass each one of them, right? So just keep going and going and going. So we have all these custom attacks. We build this box, break other boxes, right? And so I did some backdoors, and they got 0 out of 4, and some network runs, they got 3 out of 6, and did some exploits, got 21 out of 155. Mad props to HD, because HD writes all these. So HD and Todd do, so that they work pretty good. And then 5 out of 78, 33 out of 37. So I started playing with the filters, like I don't have them all on, or I don't have the right set on, and so I was like, oh, what's going on? Now I haven't even done the PCRE recursion thing yet. This is like out of the box. Like I'm like, trying to figure this out. I'm like, oh, this sucks. Now, granted, we don't have any like stored exploits. We don't use anything that's off, you know, any of that cool stuff. We just write our own, right? So they're all custom. So
That's cheating.
21%. They got 21% of the attacks, which is like I didn't even bother to do the recursion limit. I was like, I'll just go drink. So that's what I did. So, it was 21%. I'm sure recursion I could have gotten more. We did find though that if we did evade it, we put some evasions on it, it caught them. But it caught the evasion keys. So if we tried them vanilla and they worked, and when we try to evade it, they definitely caught it. And we noticed that a trend in IDSs and IPSs, the more evasions you put on something, the more likely you'll get a hit. In fact, you'll go all the way up to 80, 90%, almost all of them. But most of them get by with 20 to 40%. Just vanilla, as long as they're not, what you found off, like full disclosure, NetSAP group, whatever. As long as you don't see those, it's pretty good. I don't know if they actually release any exploits.
Have you seen any good solutions for the recursion issue?
Yeah, actually there are. In fact, I'm sorry, I forgot your name. Nick and I were talking about that. Actually, there's always a way to do it, and that's write your own regex that doesn't have backtracing and all those things, and you can actually do it. You have to write your own, but it's just so easy to grab it off the shelf, right? You just have to do it, and that gets.
It can also be changed.
Yeah. So that.
Not static.
Yeah. So
depending on, but it will affect the throughput of the box.
Right, and that's the other issue.
What you want? If you want full throughput like a typical point box, go for it. Anyway, it will just fall open.
Yeah, okay, ouch. I don't work here anymore, good. I cashed out some jackets. So, Juniper, So what I decided to do is I did this last time at CAMSEC. I was like running through and found a filter on CBS Web. Like if anybody ever uses CBS Web, you're gonna fire a filter because that's it. I was like, that's kind of weird. So I ran on this little PowerBook. I don't have a MacBook Pro. Okay. So I ran it through, and basically I want to figure out, well, now if I run it through with the filter, how do I hit it, right? So at 66 microseconds, it's got 15,000 packets per second. And if I missed it, it was great, right? Which is what you want, because if it hits it, you don't care how long it takes. That's the truth, right? If it actually hits the filter, who cares? That has no effect. That's a rare occasion, and it's supposed to be that way. It's the misses that you care about, right? You're not supposed to be slow in misses. 250,000 packets per second for a 50 megabit box. That's rocking, dude. I got no complaints. Sadly, it's the same box as the other ones. So I increased the data size to 1,500 bytes just to see what they did, and suddenly I got 5,000 packets per second. So then I did multiple streams, and I got 688 packets per second. And so all you gotta do is send one stream and keep doing, recursion. When you do a recursion limit, what happens is every time you recurse down, and it hits that limit, it says, I'm going to take too long, or I'm going to suck up too much memory, especially because they do a PCRE study, and so I'm going to get out. And so what you can do is just go down 6, come back up, go down another 6 again, and just keep going down 6 over and over and over again, and you'll get it to go really, really, really slow. So just do cbsweb.cg, cbsweb.cg, and just keep going and going and going, and just build a packet like that, and it goes really slow. So how to build your own 200, 600 if you bought 50, or if you want the VMware image of the eDonkey 9. So I don't even know what eDonkey is, but I'm sure he's sexy. So buy one super microboard, install 2, because I think he supports 2, because the kernel is compiled with SMP processing, but it only had 1 chip in it, and it was only a 1 chip board. But I bet you do have a 2 one, because I would do it for SMP unless you're a Linux distro guy, it's really lame. And they probably did 2 gigs of memory based on the memory I saw for the allocation of how they did the flow table, which are these things right here. So you can actually, they say, well, this box only does 10,000 sessions, and this box is 25,000. Well, you can actually just set them yourself, if you know the commands, those are them, and you can just increase them so you can have better boxes. I would do that, because it works. So they also have these, I don't know if you can actually get the silicon parts. I know you can get the E1000, but I actually don't know if you can get the modded parts, but they're cool. So now we're going to talk about somebody else, because it's fun. So I'll never get a job anywhere else. So example, top layer. So they're the leader of intrusive prevention. That's like a great statement, right? Just out of the blue, I'm the leader. Oh, cool. So they're all hardware, all right? So they supposedly all hardware. I thought that was awesome. So 4.4 gigabits raw firewall throughput versus 2 gigabits rated firewall throughput. What does that mean? Does anybody know what that means? Raw and rated? I really don't. I couldn't figure it out. I tried. They support 50,000 new sessions per second with a 50,000 sessions teardown per second, 1 million concurrent, 1.5 million synth flood detection rate. Did anybody tell me what's wrong with the math right there? Yeah.
Suggestion: raw and rated could be one's queued and the other one's not.
Yeah, I don't know.
Like using policy queues. I don't know if that's got QoS.
Yeah, that might be it. Yeah, I had a hard time figuring out what they meant. So 50K new sessions per second, 2 gigabits. So 50,000 per byte means they go 3.2 megabits per second. In fact, when I tested it, it only went 2.5 megabits per second. Meaning if I set new connections at it, it went 2.5 megabits per second. It's raw at 4 gigs, according to the architecture, but according to engineering, it's 2.5 megabits. Some dumbass bought one of these boxes and spent a lot of money, and then it didn't work. And you probably got DOS, and you're like, oh, let's tweak the filters. So I think it's really, really poor that that's happened. I actually think people should sue under the DMCA that this is just uncalled for marketing. I don't know if that'll work, but it could. So also, you can figure out these devices exist really easily. Most inline devices, like if they use FPGAs, the FPGA can't handle all the states, right? So if you do like TCP options, it might get freaked up on it. A lot of them change stuff, like some change CTLs. Right? So they decrement. So now you know they're there. Most of them don't anymore. Others reward TCP packets, which is great, because they put in the buffering out of order, and so they try to fix it for you. And they go, well, we're optimizing the network by putting it in the right order. So they send it out of order on both sides, and you can tell what it's doing. You can also characterize a box remotely by how it does your out of order, which is really neat. So
don't most of the transparent inline devices do some sort of sniffing for their command and control packets?
Now, most of them actually do run on a management plane. Juniper runs on a management plane. I don't think you have any command and control in the transparent. I don't think ISS even does that anymore. Most everybody runs on a management plane. They have, like, in the Juniper box, it has a separate Ethernet card, completely different for the management. I mean, because they have a pretty expensive card on the other side. So you can figure out what box it is. So, example, top layer says all the TTL at 255, which is really cool if you want to like extend the hops and keep going around and around and around and around. And all the TCP options are changed. So it's cool, even if you don't have the data in there. So that's really cool. It's like, nulls it out, which is interesting because sometimes they can put data in that you can expect. And so, I don't know what else to say. I'm sorry, I wasn't picking on ISS and Experience top layer. They're just examples. Every box has this. You can look at any like load balancer and do the stats on them. They have the same problem. You can do any router and do the same stuff. So it's just math, simple math. It's really easy to do. Every box has to trust the packet in some way. No one can forward a packet through the network, or no one can look up anything without believing something in the packet. I mean, that's just the way it is. And a lot of these protocol decoders believe the packet, or they believe some semblance of the packet, and that's the way to exploit them. You can absolutely get root on almost all these boxes if you work at it. And it's, I use it privately to make money. But, you could release those and protect other people, but no, seriously, every box can get rooted. Every one of them has a way to. And so, that's it. Oh, nice stuff. Questions? Anybody got any questions? No? Everybody going to the party? How many here from Canada? Awesome. You want to hear my ping pong ball joke? No. All right, that's it. Good night. Good luck.